Hello, how's everybody today? We're going to begin with a recursion today, and it's well, recursion is kind of a interesting concept, and we use the terms winding the stack and unwinding the stack. Because with recursion, and in fact, you probably don't realize, I've talked about the stack and the heap before, but when you call a function, that function call and everything that's inside the function, all the variables that are defined in the function, all go onto the stack. Well, again, what is the stack? The stack is memory that's automatically assigned to your executable. Now, since you're working with the Python interpreter, it's automatically assigned to the Python interpreter, et cetera, et cetera. So let's just refer to just the stack and the heap. When you declare a variable, like an integer, a number, it goes on the stack. The function call itself goes on the stack. When the function is done running, the variable comes off the stack. So here's what I'm talking about. I'm going to call main here, and I'm going to tell it to recurse. And I've just created this recurse function up here. And so if we set a breakpoint here for our program, and I debug this file, I do a step into. So this is a function call. So the function call itself goes on the stack. So we have main on the stack, and let's go ahead and get the whiteboard out here while we're doing this. And we're going to go through the PowerPoint a little bit here, but I wanted you guys to have kind of a really good foundational understanding of what recursion is, because it takes a lot of concepts that you've taken for granted. We have to discuss a few concepts that you haven't really conceptualized. And I alluded to the stack. I have alluded to the stack before, but not very much. So let's say that in main, we have a number called j equals 9, and another number called k equals 20. Okay. Main is called here. So the stack is just RAM. It's just memory, and we can visualize it as like a stack of plates. We can visualize the stack as a stack of plates. So when memory goes on the stack, it just stacks up. And then when it comes out, it gets removed. So as it stacks up, the memory stacks up, but when you come out of the function call, it comes back. Okay, so let's refer to our first call of main. And main is on the stack with what is main get put on the stack with. The function call itself gets put on the stack, and then j and k is put on the stack. So main with j and k are put on the stack. So let's just refer to that as a plate. For a stack of plates at the buffet line. Because that's how the stacks work. You stack on top of them, and then you remove from the top. And that's why we call it the stack, because it's that memory piece that's given to your process that is regimented in how it behaves, but it also describes the flow of your program. So main is called, and it's put on the stack. So we step into it. And now it's on the stack. Now you see over here, because j is something that's declared in main, when main is called, J is not put on the stack yet. So J is kind of just not there yet. Only main is on the stack. Then J is created and it goes on the stack. And we could probably put J up here. J. And then that J goes into our locals. And we call this, in other programming languages, we call this an automatic variable. So in other debuggers for other languages, you will see, instead of variables here, it will say automatics, because these are automatic variables that are automatically put on the stack, meaning that you don't have to ask the operating system for the RAM for that memory, because the stack is essentially the RAM that's assigned to your process, but it behaves in a certain way. That is first in, last out, like a stack of plates. So J goes on the stack. Something just happened. I don't know why that happened. Okay, let's do this again. Okay, main is called, it goes on the stack. J is created, it goes on the stack. Okay. So let's go back. So J is on the stack. Main is called and on the stack. I'm just going to scribble out K here, J and K down here, because they're not technically on the stack yet. All right, then what happens is the recurse function is called. Okay, so that means then that we have another bit on the stack called the recurse function call. And remember, K is not created yet. So recurse runs, and now I is put on the stack. All right, so we've wound the stack. This is what I refer to as winding the stack. So now let's look at what happens in our program. Let's pretend that there's a lot of complex, awesome stuff happening in the recurse function. And the recurse function gets done running. Well, then what happens? Well, then your program flow goes back to its calling point. But here's the thing. During that step where your flow comes out of line 3 and back to line 7, the recurse call is removed from the stack, and I is removed from the stack. It's no longer available, on the stack. It's destroyed or removed or whatever. The memory's still there. The stack is still there. You've got a set amount of memory you can put in your stack that's assigned to your process, but I is no longer on the stack. So we come back to I'm going to do a step over here. We come back to our line 7 just got done running, and we come back to the line 8. So what ended up happening is, during that time that we came back to the calling point, I was removed from the stack. The recurse call was removed from the stack. J is still on the stack. And now we put K on the stack. And so K goes on the stack. And main has access to both J and K. Well, then we do a step over again, and we unwind the stack some more, because we come back to line 10, which is here, and there is nothing else. We're done running the program. So that means that main itself, the main call to the main function, comes off the stack. And so then our whole process is no longer, our program or our script is no longer using the stack. The stack is still there. The stack has a set amount of memory. Back in the old days, I remember sometimes I only had 500 megabytes that I can put on the stack. And what would end up happening is if you repetitively called a function over and over and over, or you created too much memory, or you initialize too many variables in a function, you use up the stack, and you get what's called a stack overflow error. And that kind of in the industry is, that's kind of like an initiation point. You're actually kind of on your way to really knowing what you're doing is when you can blow the stack. So you get what's called that stack overflow error because you've put too much memory on the stack. So let's look at that, because what happens if I do this? And I can't remember what kind of error Python will do, but I imagine it's probably a kickback from the C, and we'll get some red from the C based interpreter, and we'll get some red, probably something like IO something error or whatever. So we call recurse again here. Now, well, what happens? Well, okay, let's run this. Main runs. Let's do a step into. J goes on the stack. I'm going to ignore that. And we're going to go ahead and do just talk about the function calls. Actually, we can't ignore that because it's important for understanding recursion and how it works. Because if you don't visualize that, then you won't get it. So let's what is it on the stack so far? We've got main on the stack. We now have J. We now have recurse, because we're going to step into recurse. Oh my goodness, this is okay. So excuse my scribbles. All right. Well, let's move on. Okay, so now then recurse goes on the stack. So now I'm going to step into this. Okay, then I goes on the stack. Okay. Then guess what happens? I call recurse again. So a whole nother call of the recurse function happens. So it's using up more memory. And actually, you know what? When we get into that, a whole different I is created. So let's step into that. Okay, so that recurse is called. Let's look at how that behaves. So we've got recurse called again. Then an I is created on that. Okay. Step into this. Then we start it over again, a whole nother recurse. A whole nother, I'm just going to use R for recurse. And then I. Okay, then the I goes on the stack. And then I'm going to move over here. And then what happens? Well, we recurse again. And then we have another I. Okay, so let's do this. So we recurse again, then we have an I. Okay, then what happens? We go over there, step into. We recurse again. We have another I. Then we recurse again, and we have another I. Then we recurse again, and we have another I. We recurse again, and have another I. And it never ends. So this is like a fancy way of doing loops, essentially. And there's certain problems that can be solved this way, but here's the problem with recursion and why we don't use recursion for some problem solving. And that is because the stack has limitations. you get a stack overflow because you've called recurse too many times. You've actually not limited, however, how many times you call it, and it just keeps calling itself until you run out of memory on the stack. And that's when you get the stack overflow error. So let's look at how that behaves in Python. I'm going to go ahead and just hit continue. Okay. And so Python is smart enough to detect that you have exceeded your recursion depth or the stack that's available to you behind the scenes. And that's one nice thing, because in other programming languages, you would literally blow the stack and the whole program would die and bleep out and all kinds of weird things would happen. Blue screens, you name it. Stack overflow errors would pop up as an unhandled exception. You know, and you can actually catch this exception. Yeah, you should be able to. So that's the problem with recursion, is if you keep winding the stack, throwing things on top of the stack, it eventually exceeds how much memory you have on the stack, and therefore that's why you have a maximum recursion depth, because otherwise you would get a stack overflow error. Python has an in-between protection between the executable built in C and you know, your Python script, and so it detects when you've gone beyond a certain depth of recursion. Essentially, it just sees that you're using way too much of the stack than is mechanically, or you know, that can be kind of envisioned for any real purposeful use, and says, hey, you're done. So what problems can we solve with this? Well, that depends, because there's a key thing about understanding how the stack works, and that is both in the winding of the stack and the behavior that happens when you unwind the stack. So let's go back to PowerPoint and let's go through some of that. And I just want to talk about a few things on the PowerPoint. Then we're going to come back here and I'm going to show you the mechanics of winding and unwinding the stack. Okay, so what is recursion? Number of times a function calls itself is your depth. Recursive, a function that calls itself. Here's a nice handy dandy example of a function call that calls itself a certain amount of times, the value of times that it calls itself. And this is a good example of winding the stack. And one thing that you want to make sure to protect yourself from blowing the stack is to control how many times your function can recurse. So if you examine the code that was built, that is made for this example, you'll see that inside the function message, the message, yeah, recurses, but only as long as the times that is passed to the function call is greater than 0. And then it stops the recursion. So you know, a little bit more on this when I show you about winding and unwinding the stack. We're going to come back to this type of behavior. Let's go ahead and think about, well, what are some of the problems that can be solved with recursion? Well, anything that needs massive amounts of repetition should not be done with recursion. However, there are problems that can be uniquely solved with recursion. And one of those is like the Towers of Hanoi. Fibonacci sequence is a really good one that can be used for solving uh, calculating Fibonacci numbers. It can be used with recursion. So some specific problems can be used to solve recursion in a much more, and I don't want to say more efficient way, but what I want to say is I want to say a little bit with a little bit more flair or style, I guess would be the proper way to looking at it. And and they can also be used to reduce your the amount of repetition. So when you use recursive programming for certain problem sets, it can reduce the amount of repetition if you were to use a loop to solve that particular problem. Okay, now we get into a little bit of some examples that we have here. Um, let me, because we're going to actually just come back to this. I don't want to get into this discussion. I'm going to be showing you that what I want to get into is, and this direct and indirect recursion. Yeah. I don't. Indirect recursion is when you have multiple functions being called with each recursive call. So let's say you have a function A that calls function B, which then calls function A, which then calls function B, which then calls function A, and which then calls function B. That I wouldn't build things that way. It's going to drive you insane. I have actually I've not seen. Yeah, I have seen the the Fibonacci sequence. I believe can be solved with indirect recursion. Now let's let's actually get into a little bit more on the mechanics. But this is kind of what I wanted to get to is the Towers of Hanoi is an example of an algorithm that recursion helps solve with a little bit more of that flair and and the behavior is a lot better with recursion than it is with repetition. So other than that, I want to get into the mechanics now and give you a visual understanding of what winding the stack is and what unwinding the stack is. Because that's where it's all at. Where it's all at. If you understand that, then you've got it. You can implement recursion in a couple different ways. If you have that vision. So I'm gonna come back and we'll continue on with that. Okay, we're back. So what we're going to do is we're going to kind of model a little bit from what your PowerPoints have. And we're going to modify this. We're just going to call recurse once. And we're going to pass it a counter called count. And we're going to call that I when it comes into the actual function. Okay, so I'm going to print I before winding the stack, and I'm going to print I after winding the stack. And I'm going to send 0 as the beginning count. And let's say that I'm going to continue winding the stack as long as I is less than 3. If I is less than 3, go ahead and wind the stack. And that's what line 5 does here. But what do we got to do? Well, we got to do I plus 1. So I will be added to 1, or 1 will be added to I. Then the recurse function will happen, and I will be equal to another value, 1 added to it. So we'll start at 0, then it'll go to 1, then it'll go to 2, and then it'll stop there most likely. It'll go to 0, 1, 2, because we're saying less than 3. So then what is output here in I? And every time the I is print for each run of the program. So if we are running, or the function, if we're calling the function 3 times, and every time we add 1 to I, and this is like a very simple example of understanding recursion and winding and unwinding the stack, because a lot of you would look at this and say, well, line 3 and line 6, the I values will be the same when it prints. So let's look at that. Recurse runs the first time, and let's actually, you know what? Let's get this so we can actually kind of look at the code while we're fubbing around with stuff on this thing. Okay. Okay, silly thing. All right. All right. So the first time we send 0. So 0. The first time we call recurse right here, we send in 0. We print 0 here. So 0 is print first. And then we run the recurse again of I plus 1. And what happens here? What happens here? Because some of you would say the first call of recurse, this print will output 0, and then this print will output 0. So you would say 0, 0, then the next call 1, 1, then the next one is 2, 2. Well, that would be incorrect because of the way winding the stack and unwinding works. So they would output the same value, but they would do it at different times. So let's look at actually what ends up happening. And I'm going to use R to draw a recursive call. So we send R in first, and we print, we put R on the stack, and we print 0. Okay, so that happens first. So let's look at that. In main, step into, we just put R on the recurse function R. I'm saying R is recurse here. We just said R, recurse, and we print 0. Okay, and then there's our 0 output. Then we say, okay, I is still less than 3. Let's recurse again, but let's add 1 to I. So the recurse function gets called again, and it goes on the stack. But this time, we added 1 to I, so when it comes in, it's got the value 1. So we called recurse again, we print 1. Then I is still less than 3. We call recurse again. We add I is 1. We add another 1 to it. So when recurse runs again, we're going to have 2 come in here. So I'm going to step into, and boom, recurse just happened again. But now I is equal to 2. So we print 2. So we go R, another recursive call, 2. This is winding. We're winding the stack. Winding. Okay, yeah, let's throw that in there with some wonderful scribbling. And the 2 is printed. Then we say, hey, is I less than 3? Yes, it is. So we recurse again. So I was wrong. we have a fence post error. Well, guess what? The most common error in computer science, and it's a joke that you see on a lot of t-shirts, the off by 1 error. I call them fence post errors. So we recurse again. Now I is 3. So let's go back here. Now I is 3. And we've called that recurse and printed 3 with that recursive function on the stack. Okay, so then what ends up happening now? Well, I is no longer less than 3. So now we finally reach line 6. But this is after tunneling a hole. This is after we've recursed 3 times, guys, and that's the main key understanding. Line 6 doesn't happen until we're unwinding the stack. And you get some peculiar behavior, and this is where you're able to solve problems with, I guess, flair or with or this is where you get the behavior where, you know, how you can solve problems a little bit different than just normal loops is the unwinding. And so, you know, the print stars assignment is a perfect example of this behavior and where you would put your last asterisk or stars in your print. That would be when you're unwinding. So you wind, you print your stars consecutively, 1, then 2 stars, then 3 stars. Then you unwind, you print 2 stars, then 1 star. So now we're no longer recursing. So when I step over, I'm still in this call on the stack. I'm still right here on the stack. I'm still in this call of the recursive function. So when it prints 3, when it prints coming out of the stack, when it prints I coming out of the stack, it's going to be 3. So that's when, and we see I is 3. So our output is 0, 1, 2, 3. Then we step over again, and then our output comes to 3. So you see this would be where you print 1 star. This would be where you print 2 stars. This is where you would solve a fence post problem and print 3 stars. And, you know, you might want to start at 1, then go 2, then 3, and then go back to 2, and then 1, instead of being 0 based. That might be helpful when you're doing one of the, you know, like the print stars, print asterisk. It's an assignment that's commonly assigned across all programming languages for learning recursion. So when I come back, this is where I would decide to print 3 stars. Okay, and then here's what happens. I do a step over, and here's where it gets freaky crazy, because my runtime is going to move to here. Well, why? Because I'm coming out of my previous call to the 3rd recursive call. And the third recursive call happened here. So I've printed 3. Now I'm going to do a step over. And boom, you see it just happened in a blink. You could barely tell. I just did a step over and you could have it just happened. It hit line 5 and then immediately moved down to here. And what is I? I is 1. It must have happened twice then. I must have went step over twice for some reason. Oh, we might have to go through that all again. Step over again, and there's the other recursive call. Yeah, it did go through the 2. It went to the 1. So the way Python and the debugger is showing it, it's never showing you at the end of this line. But that's what actually ends up happening is you're coming out of the previous call of recursive function and then printing. So you see that the output is 0, 0, 1, 2, 3, 3, 2, 1, 0. Let's do that again. And let's be specific on where we are going to examine this. Let's examine it on the first. Let's do it here, actually. And I'll just do a continue each time as I counts up so that we can get it right when it comes out of its first, or right when it's not going to recursively call. Okay, so I is 0 here. I'm going to hit continue. I goes to 1. We just basically ran everything until we came around back to line 5. I'm going to hit continue again. And it continues running and recursively calling. It goes to 2. This time I'm going to do a step into so that we can see that we're now at where I is 3. Okay, so we're back to where we were at here when I was talking. And now we are no longer recursively calling. So when I go down to here, it's going to finish this call, the third recursive call, and it's going to print 3. So here is where it prints 3. So it prints 3. Then this comes off the stack. And it comes back to the the third recursive call. I'm going to call it recursive call 2 because we're using 0 number based, 0 starting numbers. It's actually the third recursive call. So it comes back to R of 2, recursive call 2. So when I do a step over, it should do a little bleep, meaning it's coming out of this the third recursive call back to the second, or it's coming out of the fourth recursive call back to the third recursive call, where R is 2, or where I is 2, excuse me. Okay, so I'm going to step over. Boom, it just went back there, and it looks like we're at where I is 2. So I hover over there, I is 2. So we've actually come out of this call back to where we called recursive call 3, and now we're unwinding the stack and back it. I keep on mixing up, but back to this recursive call where I is 2, and we print I there. Stepped over, there's 2, so now we've come out of this recursive call and back to the recursive call where I was 1. So that's the idea of unwinding the stack. Is when you're winding, you still have to come out of each recursive call because the stack has to be empty before your program is done. And that's how the stack behaves. is everything that you do in your program goes on the stack. And so a function call goes on the stack. You call out recursive 0, it goes on the stack. And then any other function call, any other variables that you have in there, like I or J or whatever, goes on the stack. And your program, when it ends, as it's coming out of its runtime and its calls and the functions that you call, it's unwinding the stack and removing these from the stack. So when your program starts, it winds the stack. It's winding the stack with every function call. And when it's done, it has to come back to the original calling, which is unwinding the stack. Okay, so let's look at winding the stack. Again, because this is where the pivotal understanding is of recursion. And that's why I'm spending so much time on. Main is called, we wind the stack. Step into. Recall our first recursive call. Step into. Now here is where I want to point out that line 6 will not happen until we come out of each recursive call and unwind the stack. So we step over. You see line 6, when I do a step into, it's never gotten to. It never happens until we unwind the stack. There, we just started over with another recursive call. We've wound the stack with a whole nother function call, and still we have not gotten to line 6. We step into, we call again, and it's only when this if statement fails that we start falling back to each recursive call. Okay, so it's this idea, print, and then it comes back to its calling part, comes back to its calling spot. Okay, so how is that working? Okay, let's make it real simple. Okay, this is the behavior that I was describing. It's just like any normal function call. You call the function, it does the job, then it comes back and continues down the line of your regular flow. So it always comes back to its calling point. It always comes back to the calling point. It has to, because that's unwinding the stack. It's the very nature of what we're doing and what programming is based on. It's the actual flow of your program, the mechanical flow. So I step into that, do my job, come out and finish the rest of my jobs. So you see, I come back to my calling point. I come back to here. And then I finish out after I've called my function. Well, that's the same thing that's going on here. Because every time I call recurse, I'm just tunneling a hole or I'm winding the stack, and I never get to line 6 until I'm done winding the stack and I start falling back from my call, and then it comes back to here from its previous call. Then it does that, comes back to here from its previous call, and then it does that, then it comes back to here from its previous call, and then it does that. So that's recursion. And that's the mechanical nature of it. And that's the way that we can use it to solve problems with imagination. And that's kind of the main idea of it. Let's give you just a little sneak peek into what this looks like with the print asterisk, the print stars example, because it's the famous assignment. So I'm going to give you just a taste of it. In fact, we might even just do it. So let's see how far we get. I'm going to come back in a little bit, and we'll get into that, and then we'll be done for this module. So I'll see you guys soon. Okay, so for the print asterisk or print stars, basically you send two arguments. Actually, I believe you send two arguments to a function that's recursive. One argument is the current line number you're on, and the second argument is how many lines of asterisks to print. And it's to create a diamond pattern. Okay, and so I'm going to get you guys a little bit of the ways there, and then you're going to have to finish it up on your own. That includes fixing fence post problems. I'm not going to get to that. I'm not going to get into that depth. You guys can do that, and also adding spaces. We may get there, but let's start with the first arguments. Let's say this. Let's say lines, line number. And let's make this easier. ln for line number and L for lines. Okay, we'll just throw a little ln line number, L is lines. Okay. So let's just start with really simply sending this function 1 for a line number. And you know me, I'm going to want to go 0 based. Because I'm an idiot sometimes and I just, okay, whatever. You may want to go 1 based to fix your fence post. Start with line number 1. It may be helpful, but me, I'm obstinate that way. So the number of lines would be, let's say, 5 lines. Okay, so what we would want to do is we would want to print 5 lines of asterisks, but we would want to start our first line with 1 asterisk, our second line with 2 asterisks, our third line with 3 asterisks, our fourth line with 4 asterisks, and our fifth line with 5 asterisks. And then we go back down to 4, 3, 2, 1 as we unwind the stack. So we're going to want a for loop just to print asterisks. And that for loop is going to be based on our line number. So, oh yeah, I can't be obstinate. This has to be 1. But my loop can be 0 based. For I in range. And this is going to be line number, because the line number is going to describe how many asterisks we print for that particular line. And then we're just going to do this, print asterisk. We may have a problem there because print puts a new line on there. We may have to solve that a special way without the new line. In fact, I think we can use a we probably don't need the for loop. We can just use a special print statement, I believe, times line number. I think we can do that. Let me make sure, because I want to see if we actually really need a for loop. So let me come back and see, because I'm pretty sure we can do it this way, but I want to make sure of that, and then we'll continue forward. See you guys soon. Okay, yeah, there is a way you can do it sort of like this without a for loop, but we're going to do it with a for loop. So we're going to print how many asterisks we need for a particular line. And so I'm going to say for I in range line numbers, or yeah, line number. And line number is going to be how many asterisks that we print on that particular line. And lines is how many lines that we're going to print asterisks on. Okay, now the print statement I want is going to refer to the end as being a space. Let's just make that nothing. See if this works out well for us. And put in an asterisk there. And we're just going to test this without recursion. And what we want is we want to see asterisks all together in one line before we can continue. Okay, that's good. We just got one asterisk. Let's test this by passing in 3. And we should have 3 asterisks. There, 3 asterisks. Okay, we're good. So let's go ahead and start with our 1. Now we want to begin printing with 1 asterisk like we have. But then we want to recursively, we want to call the recurse function again. We want to call recurse, but this time we're gonna pass in ln plus 1, and we're just gonna pass through L. It's always gonna be 5. It's always gonna be 5. And we just call, and we're just changing the line number to go up to how many lines total. And every time we recurse, we print those asterisks. And of course, we're going to have a problem. Okay. Well, here's the first problem. We're not getting, there we go. We exceeded our depth. We actually need a new line at the end of this for loop. And then we're going to have things like a nightmare like this because we got recursion going crazy. Okay, let's modify this. If ln is less than, it may need to be less than equal to L. And only if ln is less than L do we recurse. So what does that give us? Okay, so you see that diamond pattern. Why is it got like double spaces there? Okay. Oh, because print has a new line and I'm putting a new line in it. Oh my goodness. We could just print nothing and do the new line. That's so silly. Okay. That's a little bit more pretty. But it's not really a diamond. How can we make that a diamond? Is there a way that we could print spaces in front? Is there a way that we can figure out how many spaces we needed to print in front of those asterisks to line them up? Because we're not drawing a diamond, we're just drawing a triangle. And we want a diamond. So how would that happen? What would you do here? Well, could you print some spaces for lines divided by 2 for each one before you do your asterisks? So that we have like 2 spaces here, then 1 space here, no spaces here, no spaces here. or something like that, how would you get your diamond? Okay? But I'm not going that far, because here's where the last bit comes, because we're supposed to print asterisks up to the amount of lines and then print them down from the amount of lines. So we simply put this back down here for the unwind that I talked to you about. So that we print stars both on the wind as we are winding up, and we print stars when we're unwinding. Okay, and then let's look at our output here. So you see how the output is? Here's the fence post. I don't like that, because there should be only one row of 5 asterisks there. So how would you fix that? And then how would you make this into a diamond? What would that look like? And there's all sorts of ways of doing this. But here's the characteristics that I want to see from this recursion, is that you're both doing something on the wind and you're doing something on the unwind. And that's where the conception of recursion is needed, and pretty much the main big idea of this whole module is that idea of winding and unwinding the stack. Okay, guys, I am going to let you guys finish this. Solve the fence post problem. Solve the spacing problem. Give me a nice, neat diamond. Nice diamond. Print it out. That would be awesome. And not only that, but let's do a nice diamond so that you can have 10. You can have huge diamonds. Let's make some huge diamonds. Let's do it. Let's go. Yeah, let's go. All right. We'll see you soon on the next video. Take care. Bye-bye.